Hi, my name is Dr. Pete. I am a PhD biochemist and a nutrition network coach practitioner and also a primal health coach. My presentation today is to answer the question, is sugar addictive? And we start right now. Now, in my first two slides, I just want to point out that there is a great deal of inertia out there by the establishment against this idea that sugar and then therefore food can be addictive. I disagree with this, and I'm going to lay out my case for the addiction today. But I want to point out that the pushback against the addiction thing has more than one level. On the most basic level, they're saying no, they don't think that sugar addiction is real. And secondly, in the case of eating disorders like the binge eating disorder, they're saying that they don't think that binge eating is an addictive disorder. So let me lay the groundwork for this. I believe we have three pieces that have to come together in order for us to have an addiction to sugar. And those three pieces are that we need a biochemical driver. We need an entry point where the substance coming in is going to be processed. And then we need signaling. We need signaling between the biochemical driver, where the substances are being processed, and the brain. And the third part of it is the brain reward system and how it is responding to the input of that signaling, and in particular, a type of signaling which is chronic. Now, I believe because of my efforts to try and understand diabetes, and in particular, in my case, a gout sufferer, to understand the biochemical mechanism of gout, eventually I found my way to Dr. Richard Johnson's work on fructose metabolism. And this is the slide that we're looking at here. This depicts basic fructose metabolism. Remember that this metabolism is happening not only in the liver, but also in the kidneys, adipose tissue, and in a very important location, the brain, in the neurons and glial cells of the brain. This is important because I want you guys to think about this going into it. We can have two levels of signaling. We have signaling that originates, say, from the liver, the taste buds that are in my tongue, for example, and in the gut as examples. But we can also have direct metabolism of fructose and the related macronutrients that feed into the fructose metabolism directly in the brain. And this can have also a consequence on the signaling. So first, let's start and talk about the biochemical pathway. So again, you're looking at fructose metabolism. Now, to keep things simple, in a standard American meal, especially if we assume that this meal is happening in the evening, we can have alcohol, hyperglycemia, right? Because there's going to be a large carbohydrate load. So the glucose load will be high and therefore hyperglycemic. And we can also have fructose coming in because of the added sugar, in particular, especially if this meal has processed food in it or something that the individual made at home that had added sugar, like many sauces, for example. The point being, and for a moment we are going to focus on the liver, we have alcohol, we have glucose, a high level of glucose, hyperglycemia, arriving at the liver along with a fructose load. Now, if we start with the fructose is going to enter the liver in an unregulated fashion, and it is going to be entirely processed by an enzyme called fructokinase. This results in a massive depletion of ATP in the liver, along with a massive depletion of phosphate. Inverse to that will be a massive increase in intracellular uric acid, which drives a signaling process that results in a rise in systemic inflammation with the formation or the activation of cytokines and other transcription factors that drive inflammation. We're going to have disruption of the nitric oxide pathway, which has implications for cardiovascular disease. We are going to have the synthesis, significant synthesis of new fat, in addition to the fact that fat oxidation, the burning of fat, is going to be significantly downregulated. So let me repeat the bit about the fat. We're going to have new fat synthesis in the liver at the same time that we have the brakes put on fat oxidation. Now, relative to sugar addiction, what are the behavioral things that are going to happen to an individual when this pathway is activated? So we have an increase in hunger, an increase in cravings for sweet food. The individual will overeat because they're being driven to literally intake more calories. They have, or they are stimulated into a foraging behavior, which means that they are going to look for even more food. Now, I mentioned that we have 3 macronutrients arriving at the liver. We just talked about the exogenous fructose, the fructose that arrives at the liver. But we also have a hyperglycemic event, and we also have alcohol. How do they feed into fructose metabolism? They do so by activating what's called the polyol pathway. This is a 2-step biochemical pathway that drives the input of glucose into endogenous fructose, which then collapses through the pathway that I just described. Alcohol has its effect by activating the polyol pathway. And if we have substrate available, and what I mean by that word is if we have a hyperglycemic event, so there's substantial glucose that is sitting in the liver ready to be processed, then much of that glucose, up to 30% of it, will be driven through polyol into endogenous fructose, which then collapses into the sudden acute rise in uric acid, which is driving the hunger, the cravings, the overeating, the compulsive eating, and so on. So what I'm describing here is a very important biological driver. The next question is, what do the connections between this driver look like and the brain? Question number 1. Question number 2, is this metabolism happening in the brain and driving the activation of a particular protein that drives the addictive state? 2 questions. Let's take question number 1 about the signaling first. This just summarizes what I just described to you. So we have an increase in the amount of hunger, intake of food, preference for sugar, by the way, which with an additional preference for fructose and so on. So let's look at the signaling. All right. So we have taste buds in our tongue that are activated for sweet, sour, bitter, and umami. Umami is a sense that has to do with savory flavors like monosodium glutamate or inosine monophosphate or adenosine monophosphate. All 3 of those flavorings, by the way, also activate fructose metabolism. And again, these are found in processed food to a high level. So in the processed food, we've talked about that a little bit not only do you have the added sugars, but usually you're also going to have these added salts, right? The MSG, the IMP, the inosine monophosphate, and adenosine monophosphate that increases savory flavor. So all of these are activating this biochemical driver. So we have the taste buds, and they have direct signaling with the brain. They also influence how much sweet that we're eating at the time that we take in. There is a drive to eat more of it. So not only, I like this taste, signaling in the brain, but also eat more of it. Then we have the liver, and the liver has signaling directly with the brain through the nervous system, in addition to endocrine. What does that mean in English? The release of hormones that also do signaling in the brain. And that signaling can influence the drive that we get to eat more or to eat less sugar, depending on, again, what's going on with this biochemical driver. And then we have the gut-brain axis. The gut-brain axis. And the gut also has sweet sensors in it, in addition to the fact that there is nutrient sensing relative to quality. It can recognize the different macronutrients and signal to the brain. So what is the point of this slide? The point is that we have concerted signaling with the brain. Now, if we focus on the food reward system in the brain for a moment, this is a very idealized description. We can break the brain into 4 basic quadrants relative to the food reward system. The prefrontal cortex keeps us focused on what we're eating at the time, right? This sweet thing that we're eating. The nucleus accumbens is driving the motivational aspect of this. So you're spooning the food into your mouth, right? It keeps us shoveling the food. The amygdala is the part that is going, oh my God, this tastes so good. I love what I'm eating right now. And then the hippocampus is taking in all of the different sensory information so that we can remember this location and the setting, so we can find our way back to this experience. So what I want to do now is draw your attention to the second level of signaling that I mentioned before. And this is the question, what is actually happening in the brain? We know that we're going to be getting signaling from the taste buds, from the liver. We're going to get signaling from the gut axis to the brain into the food reward system. But what is happening in the neurons themselves? And in this 2020 paper described from the laboratory of Johnson and Lanaspa, they describe what's going on with this biochemical driver in mice where they have eliminated the taste signaling. And there are some profound things that they found here. The one aspect that I wish to focus on is the activation of a protein in the brain of the mice called FosB. Because what they found was mice fed fructose activated in the brain due to fructose metabolism there, this protein called FosB, delta FosB, which has been implicated as one of the main drivers of the addictive state. So let's summarize what this protein actually does. So when you step away from Johnson and Lanaspa's work and you go out and you start sleuthing down on the role of FosB, what is known about this in the case of drug addiction, it is considered a molecular switch. So when it's activated, when it's induced and produced, right, and activated, this protein is responsible for throwing a molecular switch which drives the animal and also there's human data to the addictive state. This is independent of drug delivery. And what that means in English is whether or not you've injected the drug or whether you're eating the drug substance. And the main area of activation where this protein is working is in the nucleus accumbens. So what is this protein? What does the data show that activation of delta FosB do? What does it do in the brain? So it's critical for all forms of addiction. I will give you a list of drugs that it's involved in the addiction process with in a moment. It drives the addictive state. It drives self-administration. That's where you've done the drug and now you're going to go out and you're going to get more of it because you're driven to have more of it. It upregulates or drives sensitization to it and reinforcement of the experience, and it decreases aversion to the effects of the drug so that you can increase the amount that you're having without having deleterious effects. This just shows the range of drugs where we see the activation of FosB, opiates, amphetamines, nicotine, alcohol. I think the alcohol thing is really interesting here because remember, it piggybacks fructose metabolism. And in fact, we optimized fructose metabolism evolutionarily about 24 million years ago. And the alcohol piggyback effect happened about 10 to 14 million years ago on the same biochemical driver. And then at the bottom, and this blew my mind, both sucrose and fructose cause the induction and then activation of this protein. Sucrose has been shown to do this not only in animals, but also in humans. Fructose, it has been shown to do this in animals, and hopefully in the future, they'll have more data which is associated directly with humans. This slide is only meant to show you the reference for the FosB data that I'm discussing here. You can go back through the video later, pause it here, and you can look up the same paper I did. This is an excellent review on how FosB is operating in biological systems to drive the addictive state. And then similarly, this is a reference where I found data relative to humans. Now, this leaves us then with the original question, is sugar addictive? And I think that when you step back overall and you look at what we know so far, we have a biochemical driver, a beautiful candidate that is feeding sugar addiction and the signaling involved in it to the brain. So we have the biochemical driver, we have the signaling, and we have the brain effect in the food reward system. And now we have a significant protein which has been shown to be the pinnacle driver of the addictive state, not only in animals, but most likely also in humans. This is very significant. And why is it significant to us? It's significant to us because we want to know just what the heck we need to do to get into recovery. And as we've learned, if we're in the Sugar Bomb Forum, for example, or we have listened to Bitten Janssen or to Jen Unwin or many of these other practitioners, that the first thing we need is a significant food plan where we exclude the sugar and the fructose, the sucrose. And these guys even talk about limiting alcohol. And I have given you data which is fairly compelling, why you need to consider, if you're trying to get off sugar, why you also need to consider backing off of alcohol, because alcohol is feeding the same biochemical driver. And if there's one thing that we want to do in the food plan, we want to shut down as best we can the signaling into the food reward system, right? We want to quiet that down. We want to bring the sugar down, and we want to bring the alcohol down, and we want to stay that way. We want to optimize the protein and the natural fats that we're eating and keep the carbs low. And then what else are we doing? We have the behavioral aspects of this, right? The things that we're going to do in complement to getting a food plan under control, developing new habits, the oxytocin issue with being around people that we love and people that we like to be with, right? We need to look at social aspects of this, how we're interacting in groups, the strategies we're going to need so that we can remove ourselves from the addictive substances. We have to have strategies for that, and so on. And then the third part of this, after we get into recovery, then we're going to need to know how to remain in recovery, right? We want to avoid the relapse. If it does happen, we need to have strategies to prevent the relapse from happening again. And then finally, maintaining our recovery for the rest of our life. Thank you very much for watching my presentation. I've put relevant links in the show notes. We run a private support group in Discord. It's free if you would like to join us. We meet once a week, a group of people together in the struggle, and so on. Thank you very much.